Hey everybody, this is a quick start guide to R using RStudio. It's appropriate if you've had a little bit of statistics, mean, standard deviation, scatterplots and histograms, linear regression, maybe confidence intervals, and hypothesis testing. Maybe you've been doing that stuff in SPSS or Excel or, God forbid, a graphing calculator, and you've heard that R might be a better way to go. We're going to focus on doing things in the most intuitive way possible. We're going to miss out on some of the full power of R, but the idea here is we should be able to get you past some of that initial intimidation about using this package. So of course the first thing you should do is Google R and follow the links and install that statistical package. And then you should immediately Google RStudio and follow those links and install that free software as well. R is the actual statistical package. RStudio is the front end that you're looking at now that will make your life a lot more pleasant as you use this statistical package. When you first open it up, it's a little bit of information overload. You've got at least 3 panes that you'll be looking at with a lot of different information. We're going to work mostly in the console window here on the left. I'll point out some of the other stuff as we go. Some of it you'll just use as you get more in-depth in your usage of R, but won't really need it when you're first starting up. To start, at its most basic level, R is just giving you a graphing calculator. And so you can do simple arithmetic operations like, for example, 7 plus 5 is 12. You can do subtraction, multiplication using a star, and so on. R comes with a lot of built-in functions like square root, for example. Things like sine, cosine, etc. are in there. Pretty much anything you can think of exists in terms of basic mathematical functions. The name will either be your first guess or something that you'll slap yourself for after you Google it. It'll be almost obvious as your first guess. The next thing that we want to do is to start using variables. So, for example, let's define a variable x, and let's assign it to be the number 6. So the assignment operator in R is this left arrow. It's a less than sign followed by a dash. Notice, by the way, that I'm putting spaces between my variables and my operators and my numbers. That's just style, makes things a little bit more readable. R is going to ignore spaces. After I have set x equal to 6, if I come up here to the upper right in the environment pane, I have the statement that x is equal to 6. There is now a variable x that's defined with the value 6. Back over here in the console window, now I can do arithmetic operations with that x value. So for example, x times 5 will be 30, for example. Lovely. Even better, we can let variables be equal not just to individual values, but to strings of values, what we call vectors. For instance, let's let y be the vector 3, 4, 5, 6, 7. So it's an ordered string of 5 numbers. In the environment up here, I see now that I have an object called y that is a numerical vector that's 5 positions long. We can print that out, 3, 4, 5, 6, 7. We can do arithmetic with y just as we did with x. For example, y plus 5. And R will go through the vector y position by position and do that operation to every single element in that vector. So we can do square roots of that, for example, and on down the line with other functions. So potentially already a time saver, in that we don't have to repeat the function for every value that we want to compute. Many statistical operations are loaded into R by default. For example, we can get the mean of this vector y, 5, not surprising, 3, 4, 5, 6, 7. We can do the standard deviation, variance. Another one that's very commonly useful is sum. Things like min and max are also built in, and many others that you can just Google as you need them. So that's potentially very useful. One other thing before we move on, if you want to save a result of an arithmetical operation, you can assign it to a new vector. For example, let's let z be y squared plus 4 times y. So again, we have a vector of length 5. It consists of the values 21, 32, and so on. So that's lovely. R, however, doesn't really become powerful until we start working with data sets. R is a statistical programming language. It was built from the ground up in order to help us work with data. So we'll really see its full power when we actually get a data set in front of us. So now I'm going to be in the lower right. Let me make that window larger so that we can see what I'm doing a little bit better with my face there in the corner. Here we have just a file browser. And so I'm looking in my Dropbox, and I'm going to navigate down to a file that I created in anticipation of this video called flowers. And I'm going to want to load that into memory. Before I do that, I'm going to zoom out a little bit so that we're able to read the import screen a little bit better. Click on it, select Import Dataset. There's a lot of code here that you can probably ignore, especially when you're first getting started with R. The stuff that we really care about is down here. It's this line that I'm highlighting right now. So flowers.csv, that's just the name of the file. It should be recognizable to you if it's a file that is on your own system. The code here is saying it's going to read in that CSV and it's going to assign it to be a new variable called flowers. And the name flowers came up by default by just knocking off the extension .csv. So when we actually import this, like so, we're going to get a preview of that spreadsheet, of that CSV. And one other thing that will have happened is that in the global environment here on the upper right, R is now recognizing an object called flowers. It's literally a new variable that has been assigned the entire data frame. I'll zoom in one more time as I start to talk about the frame itself. So here we have 150 rows and 3 columns. This is a piece of the famous Anderson iris data set. It's 150 observations on irises from the early part of the 20th century. They measured the petal length, petal width, sepal length, and sepal width of rather 3 different species of irises. I've subsetted that set to just have petal length and petal width. So that's now in our working memory, and we can do stuff with it. Let me zoom in one more time so that you really have as much visibility as possible here. Looking at the console window. So first of all, we might want to do some work with these actual variables. For example, we might want the mean of the petal lengths. So obviously the command is going to be mean. In order to get the average petal length here, we need to tell R 2 things. First of all, the data set, that's flowers. By the way, R is giving us suggestions as we go, potentially saving us some typing. So I'm just going to arrow down to flowers and hit enter. Now R knows that we're working with the data set flowers. We have to tell it what variable. We specify the variable with a $sign. So flowers, data set, $, now the variable. And let's do petal length. So now it's going to give us the mean petal length of all of these flowers, 3.758. One other command I want to point out right now is correlation. It's COR. This is going to require 2 different variable names. So flowers, $ petal length, and flowers, $ petal width. And in this case, we get a correlation of 0.963. So a pretty strong correlation between those 2 variables. One other command that's really nice to know when you're working with data frames is the summary command. And if you feed a data frame to summary, it's going to give you back some information about each of the variables within that data frame. So in this case, we have 3 variables, petal length, petal width, and species. The first 2 are numerical, and so it's giving us a 5-number summary plus the mean for each of those numerical variables. It gives us a little information about species as well. However, because that's a character vector, there's not a whole lot interesting that it's telling us. Character vector just meaning that the entries are letters and words. Great. So the next thing we'd like to be able to do is to get some attractive graphics. In order to do that, we're going to want to use the ggplot2 package, which is contained in the tidyverse suite of functions. The first time you load in R, you should type in the command install.packages quote tidyverse. This is going to download a whole set of functions and install them on your machine. These are going to make your life much better when you work with R. Trying to do things without tidyverse is just a little bit harder. It'll go relatively quickly for me because I've already installed these previously. For you, this might take a few minutes. The good news there is that you only have to do it once. Now they're installed on your machine. However, every time you open up a new session of R, every time you restart this the program, you have to let R know that you actually want access to those functions that you have installed. The way you do that is with the library tidyverse command. And so again, you'll need to do that every time you want to do graphics and data analysis in the way that I'm going to do it from here on out. That'll only take a second. So let's start by getting a histogram of the petal lengths of all the flowers in this data set. The way we're going to do it is with the qplot command. That's our beginner's workhorse function for graphics in R. There's more sophisticated ways to do things using the ggplot function in particular, but that's, I think, less intuitive when you're first getting started with this stuff. So qplot for a histogram is going to require one variable. A histogram is a one variable display of data. So we want to do flowers $petal length. Notice that we haven't specified that we want a histogram yet. We've just said that we want a plot. R already knows that we want to put petal length on the x-axis, but it doesn't know how actually to display the data. So we need to tell the system how to display it now. The syntax for that is geom, G-E-O-M, equals quote, and then the name of the display you want, the name of the sort of graph you want. So histogram. Okay, so in the lower right, you're going to have a little preview. My face is going to be blocking some of it, so let's zoom in on that. There we go. It's already a reasonable looking graph, although it's not yet at professional quality. First of all, I notice that the labels are bad. The X label there, flowers $petal length, is literally just the name of the variable being graphed, the technical name of the variable. So we'll want to put that in human language. There is no Y label, so we might want to add that. And at some point, we're going to want to be able to do some things with colors and so on. I'll talk about that part of it a little bit later in this video. So let's close this and go back. Also notice we have this warning message, the using bins equal 30. Let me comment on that right now. So it immediately tells you how you can make that warning go away. I'm going to use an up arrow to get the previous command. It's a nice little shortcut to save some typing. Suppose that instead of 30 bins, I only want 20. I can do bins equals 20. And it'll give me a very similar looking graph, but with the data split up a little bit differently. I'm just going to erase that command so that I'm not seeing it anymore. If you prefer, you can, instead of telling R how many bins to give you, you can specify the width, and R will compute the number of bins needed automatically. Next thing I want to do is to fix those labels. So if I want to change the label on the x-axis, the command that I need to add into the qplot command is xlab equals quote and then the name of it. So how about petal length? So that looks a little better. We could add ylab, for example. So the reason for the syntax of qplot with the geom inside, which seems a little awkward at first, becomes apparent when we decide to switch from a histogram to another single variable plot, like a dot plot or a frequency polygon. Let's see how to do a frequency polygon first and see how similar it looks. So I'm going to use the up arrow to get the previous command. And I'm just going to go and change the geom equals histogram to geom equals freq poly. So this is a very similar graph. It's got the same x value being plotted left to right, and it's still got counts going up and down, like so. The basic idea here is that when we're specifying the x value and when we're assuming counts are going on the y-axis, the plots of a histogram and a frequency polygon and a dot plot and several others are all going to be fundamentally similar and really don't need to have different commands. And in fact, it's best for us intellectually to view these graphs as really of a piece with one another. Close that window. So I encourage you to explore the qplot command using the same syntax here, just with other geoms. Geom equals dot plot and geom equal box plot are two good ones to play around with. The next thing we should do is to look at scatterplots. So again, we're going to be using the qplot command. A scatterplot is going to be a two-variable plot, so we need to specify two variables. So let's put the petal width on the horizontal axis, and we'll put the petal length on the vertical axis. For a scatter plot, it's geom equals quote point. Let's zoom in on that. There we go. So it's a scatter plot just like we would want. We already know how to change those labels on the x-axis and y-axis. One thing that's really nice about the ggplot package here in the tidyverse and about the qplot command is that we can add color to this graph in a very direct way. In particular, notice that in this data set we have this categorical variable species, and we have three different species of iris. We have setosas, versicolors, and virginicas. So one thing that we might want to do, for example, is to get these points in our scatter plot to be colored according to their species. So I'm going to add an additional argument here. Just as I put the petal width on the x-axis and the petal length on the y-axis, I can put species mapped to color. So I'm going to type color and then the name of the variable that I want to use to define color. So in this case, it's flowers, if I can spell it right, $species. Let's see what that looks like. Now we're starting to get something that's looking a little more professional. Obviously, we need to change the labels a little bit to make this look a little better. Now the setosas are given pinkish red dots, the versicolors are given green dots, and the virginicas are given blue. Already, we're getting some insights into this data set. We can see that the setosas tend to have smaller petals than the other two species, and then the other two species are somewhat clustered together. So the next thing that we probably want to do if we're looking at scatter plots is to add a regression line. So just for simplicity, I'm going to remove the color from this graph right now, go back to the slightly less visually appealing plot that we had before, and try and add a regression line. So when I say add a regression line to the plot, one nice thing is that the syntax in R is going to directly reflect that sort of addition that really is happening, the layering that's happening. So I'm going to take that ggplot command, and at the end of it, I'm literally going to add in plus geom underscore smooth. So let's add a smoother. There are many ways to do this. The simplest and most intuitive, at least when we're starting out in statistics and reading graphics in particular, is a linear one. So let's do method equals quote lm. So that's for a linear model. And when I hit enter, the new graph is going to have a regression line, like so. Notice the error ribbon there, that sort of gray shaded, gray shading around the regression line, which is in blue. So that's an error bar representing confidence intervals for that regression line. If we don't want that, we don't have to have it. We can add another argument to our geom smooth right after the method equals lm. It's SE, standard error bar, equals false. So as in, don't put that in the plot. And I must have mistyped that. Yes, SE, SE with just one E. And so now that error ribbon is gone. One other thing that we can do, for example, is right away is to get that regression line with a different color. So how about color equals, how about red? Okay. So obviously there's a lot to play with on that. You can change it to many different colors. What happens, by the way, if we leave out the method command? And I'll go ahead and take out the color while I'm at it. Let's just see that really quickly before we stop. So it's giving a warning message about what method it's going to use. R's default method for smoothing is a low S curve. So it's giving you sort of a higher degree polynomial that is done using a rolling window. It tends to fit the data a lot better. It's less intuitive to understand exactly what's going on there. You also do have a greater risk of overfitting. So I encourage you, when possible, to use linear models for simplicity, unless they're not called for some particular reason that you are specifically aware of. A couple other things that I want to show really quickly before we wrap up this video. First of all, let's go back to that histogram that we saw a little bit earlier and make it a little bit more colorful. So our command there was qplot, then the variable name was flowers, $petal length, and geom equals, quote, histogram. Okay. Now, so the initial thing you might want to try is color equals, quote, red. Natural enough. Let's get a histogram with red bars. And that will give you an output, but it's not going to look exactly like what you would expect. Notice that it gave you a legend with red as sort of a variable name. The reason is that, as we saw with that scatter plot, R with the ggplot is defaulting to assuming that color is going to a variable name. So if you actually want the literal color red, you're going to have to specify that more explicitly. Let R know that you are not giving it a variable, you're actually giving it a color. So we're going to enclose the color equals red. We're going to enclose the red part in I parentheses. So identically, give me red. And now I will actually see red. Notice that color for the histogram is just giving you the sort of surrounding part on the bars. If you actually want the bars themselves to have a different color, the command is fill. So let's see what that looks like. So this time I will do fill is red. F-I-L-L. There we go. You can use both of those. So for example, just for my last one on this scatter plot, or rather on this histogram, let's do a fill of red and a boundary color of, how about black? Okay, so there we go. So it's starting to look a tiny bit more professional, and if you have any graphic design capabilities, you can make your you can choose your colors a lot more intelligently than obviously I am. Two other things I want to show. First of all is a tiny little bit of statistical inference. We have petal length, for example, here. What if we want to get a confidence interval for that? So the command that we want to know there is t.test. And then we'll feed it the name of the variable, flowers. $petal length. Okay. So it's immediately spitting out a 95% confidence interval there. And it is, by default, doing a t-test with a null hypothesis that actually the population mean is equal to 0. So true mean is not equal to 0. The confidence interval is going to be good regardless. In this case, it's not going to make sense to do any kind of statistical inference with a true mean, with a null hypothesis, or rather, a null hypothesis that the true mean is not equal to 0. We could specify a different null hypothesis if we want. So t.test mu equals, say, 4. Okay. In that case, we get a p-value of 0.09525. One other thing to notice here is that it's going to default to a two-sided alternative hypothesis. We can override that as well. Alternative equals, quote, how about less? There we go. And so now, as you would expect, the p-value is cut in half. So there's a lot more sophisticated statistical inference that can be done using R and RStudio. We're not going to get into that here, of course, but that is another direction for additional exploration. The last command I want to show is the filter command. Frequently, you may run into a case where you have a data set and you don't necessarily want all the data. Maybe there are outliers, or maybe you have a set with 3 different kinds of flowers and you only want to analyze one of them. So let's take this flowers data set that we have and get another data set that only has the Setosa flowers. So what we want to do is get a new data frame. Let's call it flowers underscore Setosa. And we are going to filter the flowers data set. And we only want to keep the ones for which species, is equal to, quote, Setosa. So notice that I used a double equal sign here. That's R's notation for logical equality as opposed to assignment. So now in the upper right hand in the environment, I see that I have another data frame now with only 50 observations. Let's use the view command, capital V-I-E-W, to look at that. So let's view flowers 2. Did I give it a different name? Looks like I might have given it a different name. Oh, flower Setosa. Sorry. So flowers underscore Setosa. When I was practicing this video, I did it flowers 2. Okay, so there it is. It's going to be exactly the same data frame, except now we're only going to have 50 entries, and they are all going to be Setosas. R has a great many other data wrangling functions available. Filter's the first one that you really should know.